We seem to be live. There's actually a major input of people somehow between now and 10 minutes from now. or there was. Maybe we'll get to the, if there are fewer people here than there were homework submitted. So that was, anyway, that was, given my policy of, the homework is for your own good, it's good to see you do it. So I'm really glad to see you turning in the homeworks and just proceeding normally. And I hope many of you will keep going to the recitation. I hope you've, Ieorertsj, the TA is, I think, really good. I think you can benefit from that. Of course, the main thing is to be doing, I think, as I said before, the main thing is to be doing these problems yourself. The course is about problem solving. Doing the homework yourself and working that through is the bulk of the course. And if you do that, you'll be okay. And if you don't do that, you won't be okay. And hopefully the other stuff is worthwhile. But it's sort of almost, it's sort of irrelevant, but hopefully it'll give you a feeling for the subject that's sort of different from what's tested. But the tested stuff is like being able to do those homeworks. So hopefully there's some connection. So I'm sort of like a coach in some sport that may or may not add anything to the performance, right? It may or may not be help. But anyway, there are things other than just the problem. Okay, well, I have two topics for today. Let's see. So we're going to learn about project management, and then we're going to consider Markov mouse. But we're going to view project management from the perspective, typical Columbia perspective, perhaps, from a kind of theoretical, probabilistic perspective. So all the mess and the reality of project management, like if you're thinking about if you've been down on the third floor on our office space, we've been renovating our space. So last year we renovated the right side, and this year we renovated the left side, and there's all these different things that have to get done. And of course now they're fighting the stuff that didn't get done right, and the people who did the different things are fighting about whose fault it is that it didn't get done right, and the stuff. So the reason we're here still, because the classroom is supposed to be 301, is that somehow the microphone, the system for CVN isn't set up right in that room, even though they're using that room for non-CVM classrooms, but the connectivity to CVN isn't right. And and that evidently could be corrected in one day, but it's they're squabbling over who's responsible and when can they get access to the room and so forth. So there was guaranteed, this is as I would have predicted, but it was guaranteed that we would be in that room at the start for all these courses at the beginning of the term. No issue. I actually requested one of these CVN rooms for my classroom in the anticipation that their guarantee, very strongly expressed, would not be realized. So, I mean, what do I get? The satisfaction of knowing that I was right. What is that worth? What is that worth? Okay, nothing. Okay, so that's sort of like real project management is kind of complicated, messy. It has a lot to do with people interactions, and if you interact well with people and communicate, these screw-ups won't happen. And that's not what I'm going to talk about. I'm going to talk about a sort of simple view, but actually could be important. So, and well, this sounds important, this sounds unimportant, but things may not be quite what they seem. So this is the menu for today. So I guess we're going to start. So my take on project management is not like The IRR space renovation is a typical project of which there's lots of things, and some things go in different orders. I want to consider sort of a simple view of project management that actually would be the kind of thing you might do, or an industrial engineer might do in a real situation, to do some sort of calculations on the side to see if things are reasonable, right, that you could think about. So I'm going to think, well, we've got a project, and it's going to have 4 or 5 steps. And each step takes a random time, and we're going to assume that the steps are independent. I mean, that you do one, and then when that's done, you do the second. When the second step's done, you do the third, and there's not overlaps. It's overly simplified, but the thing you're going to focus on is that the time it takes to do each step in the project is random. There's issues coming up. So you're going to do step 1, step 2, step 3, and you're not going to start step 2 until step 1 is done, but step 1 is going to take some random amount of time. So you model that somehow. And step 2 is going to take some random amount of time. And there's going to be, say, 4 steps. And they're each going to take a random time. And you're going to, for simplicity, you're going to think of maybe they're done by different contractors, subcontractors, or whatever. So you think of each step as independent of the other. So they'll just start when the other's done, and it'll take a random time, and you have some idea. So you're going to have some random variable for each of the steps, how long it's going to take. And then you want to know how long the project as a whole is going to take. And maybe that's something, you're going to do something, you're going to borrow money and pay it. You're going to do something that requires that you know how long the whole thing's going to take. Like you're going to, at the end of this time, you're thinking you're going to use these classrooms for something. Whatever it is, you're going to. So the model of the time, the overall time, would be, well, let's just be explicit. There are 4 steps. The total time is the sum of 4 random variables. We treat them as independent. So we're going to think of them as independent. And this is not the realm of Brian Greene. These are all non-negative times, right? Each time is going to be a positive. They're non-negative random variable. And we're thinking, what we want to know, we just want to know, we're going to model these. So we're going to use our experience and insight and understanding to represent each of these as random variables with some distribution. And then given those, we're going to want to know the distribution of the time. So we might want to know the probability that the total time is less than t. So this is the cumulative distribution function. For any little t, we want to know the probability that the project completion time is less than t. Well, of course, so that's the thing we want. We want that for various t. Now, just to be a little bit practical, you might think of these things, well, what do we know about these? So you don't want to know too much. I mean, I'm thinking you're going to know a probability distribution for each of those, but to kind of even be a little bit more realistic, to think about what we might know, we might sort of have a mean and variance estimate. I mean, that's just going to be kind of rough. So you're thinking, well, maybe the time should be this long, and maybe it's something. I don't know. You have some, that looks sort of normal, but you have some time, and then there's some spread. So it might characterize the time. I mean, the distribution might be sort of funny, but you might think of this somehow as one of these. So let's say FI. T would be the PDF, probability density function, for the time of one step. Might look something like this. But what you're going to know maybe is you're going to know the mean and the variance. So this you might say, and that's sort of, or the standard deviation, which you could square to get the variance. So you're thinking it's some shape maybe like this, and you know the mean and variance for each of the steps. So what I'm saying is this is actually kind of like what you might do. You might roughly estimate these things, and you might actually have some idea that that this might actually look something like this. You might actually say, well, there's something weird that could happen. It's either going to take this or it's going to take that. Right? I mean, there could be things where you see that there's a critical thing in this step. If things go right, it's going to take some random amount here. But if things go wrong, it could be a lot more. So there's sort of two possibilities. You know, there's probability P that you're in this thing and 1 minus P. So the density, overall density might not look like this. It might look like this. So you're going to have F1 of T, F2 of T, F3 of T, F4 of T. And you do something for each of these, you're going to somehow fit, these are PDFs. These are the densities, the probability densities of the time to do each of the 4 steps. And you use your judgment. It might look like, in other words, the overall picture, the density might look like this because of the fact that there could be, you think, well, if with probability P it's going to be okay, but with probability 1 minus P I'm going to have this, and so the density might look like this. This is your idea of how long it would say the second step density looks like this. So you use your judgment and make it look like that. You have some... now the thought is, how... Well, so I'm actually trying to make this a little bit real, and I'm trying to actually think about how I could do this stuff. I mean, I might actually... how I might construct these. So I might have these. So what I'm trying to say is, well, if I was just doing this roughly, I'd have estimates of mean and variance. So the sort of kind of a procedure you do from a practical engineering approach is, for assuming that I don't have this, if it's sort of like this, I would then fit some distribution that's sort of reasonable with this mean and variance that I've now estimated directly. I might think, well, the mean's this, plus, you know, and I have to think about plus or minus to learn how to think about variance, but I specify a mean and variance for each step. And then I fit some distribution to it. So an easy distribution is gamma. Gamma is easy. It has 2 parameters, so the 2 parameters can be related to the mean and variance. Now, gamma is nicely, well, it's nicely characterized in terms of exponential, but it's got a funny distribution. So transforms come into play here. So the point of all of this project management, by the way, just to stop all this sort of discussion of reality, is I'm completing the discussion of transforms. And actually what I'm doing, this thing is not going to move far, so I'm focusing on transforms, and I'm focusing on Laplace transforms. And I'm going to ultimately focus on numerical inversion. And then this is the end of the probability review, and I want to talk a little bit about these. And you'll see that I've gone totally nuts on the web page. If you've been looking at the web page, you may be suffering from fear and loathing, because you'll see that I put up all these extra credit projects, one of which is inversion, and there's some notes and so forth. I'm not going to keep doing that, you know, like at an exponential pace to put on 6 projects today, and this is probably the end. So I've just put these things up at the beginning to give you time to think about it. So there's a project on this, on numerical inversion. Now, on this subject, there's very little in the textbook, like 1 or 2 pages on moment generating functions at one section. There's a little bit in my notes. For the purpose of the course, you don't need to do any more than that. And the stuff in the book is enough. But if you want to know more, you certainly can look at all over the place. Books have stuff on all these transforms. So you can Google, go to the library, look at a probability. But you could find more. You could easily want to see more than you see in Ross. Okay, now the moment generating function is this. So this is the moment generating function. And the Laplace transform, well, this really looks stupid, say. This looks stupid. What the heck is the point of this? It's just, instead of that, we have minus s here. It looks like there's, all these transforms are very similar. So that your reaction is, indeed, there are a whole host of transforms. There's Many, many. So if you find some book, encyclopedia of transforms, it'll have 30 chapters with different transforms. It'll have 30 different transforms. There are certain main ones, 4 or 5 main ones. Moment generating function is one, and Laplace transform is another. And then in the terms of the transform, if I did it this way, I would have written this is the conventional notation. I have a function f, and the Laplace transform is f hat of s, where I'm taking the Laplace transform of the function f, and I get this other function of s. And now, the point that's a little tricky is s is a complex variable. That shouldn't freak you out in engineering. That should be something that is a help. This is a help, not a hindrance. Complex variables are not meant to be cause you grief. They're meant to be able to solve problems amazingly for you. But anyway, it's not going to be important. It's just it's there. So when the Laplace transforms are nice for non-negative, this takes place on the. Notice this definition here is on the positive real line. So this function is really only defined on the positive real line. And so for our purposes, this function f is the density. This is the PDF. And so this random variable should be non-negative. X greater than or equal to 0. And that's just what we have, and what we often have in many OR probability applications. The random variables are non-negative, they're times, so forth. So they're like this problem, they're all non-negative. So Laplace transforms are great here. Yeah, is this a question or just stretch it?
No, question.
Good.
What, for a non-negative random variable, what exactly is the difference between Laplace transform and MGF?
Yeah, so one fundamental question that's one fundamental question would be, this looks the same, and why would you? So let's discuss sort of, this is the high-level question. Here is this thing, fine. Why would you want this thing? That's your point of fundamentally, what's the difference? If this was, this could be any complex number, so in particular, this in general could be, s could be minus t, and it would be just this. So we're actually, the problem with this is very simply, this thing, if we wrote it down, if I write it here also, if I wrote down what this is in terms of the fx of x, the density, right? In terms, if I wrote it down that way, I would have written and of course, if this density is non-negative, that's this. So this is just the same thing as that, because if this is non-negative, then it's this. And this is just minus s instead of t. And s is complex. So so far, there's absolutely no, now we're going to start to think about why would we want to do this instead of this? And there's there has to be an extremely important reason. And there is. If this thing, notice this thing, this part grows fast. That's exponential. As x getting big, this is getting big. If this thing doesn't decay fast, this thing's going to be infinite. So in particular, suppose this is a over 1 plus x, something like this. This goes down like some 1 over x, but this grows exponentially fast. And this integrates something that's going to, overall is going to infinity. This is going to be infinity. This looks nice. This looks clean. But lots of times it doesn't even exist. When it does exist, you might as well use this. But if you do just the characteristic function, we just stick I here. Square root of minus 1, complex variables. This makes this the characteristic function. When you do this, just stick I here. This always exists for probability random variables. Always exists. This sometimes exists. So therefore, when you're doing general math, you want the one that always works. This is the main idea. When it exists, they're really the same information. Okay? And now what do we do here? This is a complex variable, but we work with the complex variables for which S has positive real part. So then think of this as a positive number. Then this is not e to the plus tx, this is e to the minus tx. And therefore, it's always finite. Okay? If I make this minus t, which is one possibility, I don't have the imaginary part, but if I make it minus t instead of plus t, this problem goes away. Now, it's actually, the next problem is more subtle. The first problem is e to the plus tx is getting big. Okay, that's easy to understand. The subtle problem is that e to the minus tx for real t is not good enough. The complex variables gives you a lot. The complex variables gives you extra structure that's hard to explain. That's a much deeper issue of why are complex variables very important is harder to explain, right? I mean, they're powerful. You get a lot by expanding to the complex plane, and your variables produces a lot of stuff. But anyway, we're not that's a fact, but we're not going to really sink into that. Okay, so we're going to work with, and so if we do something like, I mean, we're going to now consider the case of an exponential distribution. So when we calculate the Laplace transform of an exponential or the moment generating, those two things are essentially the same calculation. So if we do it, if we have f of x is equal to lambda e to the minus lambda t, or x, for x greater, this is an exponential density, and when we want f hat of s, we're doing e to the minus, now it's the Laplace transform. So I make the variable of, this is the t here and the t here, and I'm going to get the s. So I'm integrating out, but it's easy to see this is, right? I mean, the lambdas factors out, and I group the exponentials together, and I get this. And if it was the moment generating function, it would be minus t down here, which is what Ross has an example of. Okay, there's the Laplace transform of the exponential. Now, the great thing, one of the great things about transforms in probability is you often have in probability this kind of situation. You often have a sum of random variables. And actually, this is very complicated. So one approach to this problem, if you approach this directly, you run into difficulty. But if you approach it with transforms, it's easy. That's the whole point. So this is, and now I'm actually got two problems on the table. One is I want to approach this problem, and the other is I'm thinking about fitting these things, which I've left, which I was moving toward. And I'm actually going to fit by a gamma. So a gamma, its transform looks like this. It's some power of an exponential. And the mean is alpha over lambda. And the variance is alpha over lambda squared. So this has two parameters, and I can fit the mean and variance to these two parameters. That's the point out. Now, what does this look like here? The fact that this is the power of this, I mean, think of it as an integer. If this is an integer, this power corresponds to really the gamma random variable. It can be thought of as the sum of exponential random variables. When alpha is not an integer, that doesn't quite make sense. But if this was an integer, it would be the sum of exponential random variables, and that's what's going on. But this is gamma. So when alpha is 1, it's exponential. So alpha could be anything. So alpha and lambda are positive numbers, and you can see, so the thought here is Given a mean and given a variance, you pick alpha and lambda, and you've got a gamma distribution. So that's this. How do you proceed here? Well, if I only know the mean and variance, I fit a gamma. And the gamma has this transform. So it's easy. The transform's easy. So just say and if I need to do this, I could be taking the mixture of two gammas, right? If I think this thing is one gamma and this is another gamma, I could construct a mixture of two gammas. But let's leave that for the moment. We'll come back to this in a second. Let's now look at this problem head on and with transforms. So the point is, if I started with this information, I could have fit gamma densities. But now let's suppose I actually have these densities. Here they are. I've got them. Actually, they're in the form of transforms, but suppose I actually had them straight away, which I could do for gamma, which is gamma's kind of messy. So I have them. How do I do this? So let's just think about this. The probability that t is less than or equal to t equals, well, certainly that's this. Right? If I put the density of capital T here, this would be this. And now if I write this down, it's sort of recursive, let me put well, let's see. I want to use, suppose I have x1 is f1, x1 plus x2 equals g1 is g2, x1 plus x2 plus x3 is g3, and x1 plus x2 plus x3 plus x4 is g4. So what I mean here is I know that the density of x1 is f1, and the density of x2 is f2, but it's over there. But I want to talk about the density of x1 and the density of x1 plus x2 and the sums. So these are the PDFs. The G1 are the PDFs of the sums of the first 1, 2, 3, and 4. Okay? So then what I want to write is this would look like, right, because the sum of all 4 has PDF G4. Just by notation, because I want to talk about that. Now the point is G4 right? So this first is to say that the CDF is just the integral of the PDF. That's all I'm saying, this first line, right? The CDF is the integral of the PDF from 0 to t. Okay, this second line is saying that the PDF of the sum of all 4 is the PDF of the sum of the first 3 being in here times the PDF of the last one being x. So if the last one is x, the previous 3 must sum up to be t minus x, because the sum of all 4 is t. And I'm finding that this is the probability density that the sum of the 4 is t. That's the density of 3 of them, the sum of the first 3 being t minus x, then the fourth one being x, and I integrate over x from 0 to t. So this is convolution. This is saying that t is the sum of x1 plus x2 plus x3 plus x4, right? It's the sum of the first 3 plus the fourth one. And this is a convolution integral. So all that I'm writing down here is basic probability. When you want to find the distribution of the sum of 2 random variables, you use convolution, right? This is convolution here. This is a convolution integral. It's giving the probability density for the sum of 2 random variables, where one of them themselves is the density of the sum of 3. So if I proceed with all the remaining steps, I will get an integral for G3, and another integral for G2, and an integral for G1, and there'll be 5 integrals here. The answer will be the 5-fold integral to get this. That's the answer, 5-fold integral. And then I have to plug all these these densities into the fivefold integral. That's the direct expression for this quantity here. The point of this is not great. The point is that's kind of ugly. And that's where the transforms come in, because the transforms are much easier. Okay, so let's consider that instead. So now you say, well, what about the Laplace transform of this? What is that instead? This is going to be easier. By definition, this is this. That's the definition. Just the sum of t is the sum of these four x's with expectation. Now, this is, if I write it this way, let me just rewrite it. I'm using the fact that the exponential of a sum is the product of the exponential. So I'm still sitting here, I have this. All I've done is, everything here is simple. This is the definition of t. It's the sum of these four variables. And this is saying that the exponential of this sum is the product of the exponentials. I haven't done any probability. The e is still outside. No probability yet. However, now, because I assume that these random variables are independent, the expectation of the product is the product of the expectation. So this looks like and that looks like right? So the Laplace transform of this sum of four random variables is simply the product of the four separate Laplace transforms. Boom. So the transform, and if they were gamma, if these were gamma, let me move it up to here. If they were gamma, this would be lambda 1 plus s alpha 1. This is the gamma with parameters, these two parameters. This is gamma with these two parameters. This is gamma with, and then so what I'm saying is, if I said, oh, I've got the sum of four independent random variables, I know their means and variances, I fit them to gammas, that means I fit them to these things, here's the transform of the whole thing, totally given in front of you. Yeah. No, that's right. They have different parameters. Yeah, if they're identically distributed, perhaps that convolution integral simplifies, right? But if they're not identically distributed, that five-dimensional integral is not going to be easy. You can probably, at some point you can do it, and at some point it's going to get hard. This is just an easy example. So maybe it's not, I'm not saying you can't do the five-dimensional integral. You can probably do it. But this is easier. This transform is easier. In other words, I've got the transform sitting right in front of you. All you have to do is match the parameters. You give me mean and variances. We solve easily for the parameters. Then we have the parameters of the gamma. Here are the transforms. So we're done. This is the transform of t. No further calculation of the transform. But you don't want the transform. You want the distribution. So that's where we come to this. And this is the thing that's worth knowing, and this is one of my specialties. So therefore, I invite you to learn this, because you may very well, a likely situation for at least 25% of you, you've had a lot of probability. Everything I've said up till now, you know totally. That's a totally reasonable reaction. It's review. Everything's clear. However, it's likely you have no idea what to do now. And that's why I'm inviting you to learn this, to do the inversion project, because it's actually easy. Okay? the invitation. That's the extra credit project here, is to, now actually it looks more daunting than it is, because there's 3 or 4 papers there, and altogether they might be 100 pages. The thing to realize is if you read the first short paper, which is 10 pages, you'll see on one page, on one part of one page, the code written there for the inversion. And the inversion itself is actually simple. So I will write down, you can represent the inversion this way. Now this is not, you want to know, you've got, let me restate the problem here. We've got some function, ft. So the Laplace transform is by definition so we integrate over t. We're going from f to f hat of t to f hat of s, right? So this is the transform. We want to go the other way. And here's a formula. Now, what I'm putting down here, and you'll see this is in the papers, this is one formula. So what I'm saying, well, given f, given a PDF or some other function on the non-negative real line, here you go, you form the transform. But given that transform, which might be this, stick it in here. Now, this is the real part. Remember, S is complex. So you put real part here. So somehow when you do work with this, you want to be able to work with, you want to be able to insert this function and regard S as complex variables. That means you want to use some language can handle complex numbers. C++ would be fine, MATLAB is fine, so forth. But you want to work with complex numbers, and this is the real part. And now in here, S is gone, but this I here is the square root of -1. So there is a complex number sitting here, only I. We got square root of -1, but because that complex, this is a function of a complex variable, so we take the real part. So once we take the real part, this is just a real integral. Yeah. B is some number. So B is some number. It's some choice of B is important. Actually, the idea is easy to see. E to the bt sits here, and B is in here. This looks, you want B to be not too big, because it's going to get, if B is large, this is going to be a big number. So if for any t, you want this not to be too big. On the other hand, you want, and from another point of view, you want it small. So this is a parameter. Yes, this is a parameter sitting here of the algorithm, because B doesn't, you don't care about B anywhere. And then for any positive B, this is a valid formula. So then the B that you're going to use, B is one of the issues to, is any B, this is okay. Positive number, real number.
The same answer for every B.
Yeah. Now, the point is, though, if you think algorithmically and not just mathematically. So it's very important here, see, one of the things that's, it's important to think, often to think, how are you going to get the final answer? So sometimes, like I made the point before, that when you calculate a binomial, and there are terms with, it's got n factorial, and you're sticking in 1,000,000 factorial or something, right, when the coin tosses, this is a little stupid, right, computationally. You don't want to do that. So in some sense, you don't want to think just, I've written down the answer when I've written some formula down that's correct. You want to know, if possible, you want to know the answer numerically without doing any computation. That's simple approximation. Or here, you want to make sure in the end that you actually can compute the number. So this is not the answer. This is the starting point, not the answer. This is not the algorithm. In other words, I wrote this down. This is a correct mathematical formula for any B. The issue is you got to compute this. And now if you choose some random B and you stick a transform in and you just go integral on your computer, you may very well be okay. On the other hand, you may not. So the point of the algorithm is actually the whole point of these various papers is starting here. What do you do to make sure you get answers that are correct and accurate consistently? This is not the end. This is the beginning of the inversion stuff. This is a variation of a classical formula. The question is, how do you make sure that in fact you can actually do the integral? Right? So your point B is, your question is totally reasonable. B has nothing to do with it, and for each positive B, this is a valid formula. The issue next, where you read the paper and you figure it out and you try it out, is how to calculate this, how to do this. And roughly the idea is, there's sort of, what would you think of doing? What you would think of doing is roughly the right answer. Well, and I mean, this is if you can't just push the button, right? Pushing the button is totally reasonable. Someplace there's an integral button and you just bam, and you don't know anything and it does it for you, okay? That may be good. If it's not good and you had this, and you had to, like your bare hands, you would say, well, I learned that an integral is just the limit of a sum, so I could discretize this and make a sum. Then you'd see it's going from 0 to infinity, so whatever I do, whether I integrate or whatever, this doesn't look right for finite calculation because it's going from 0 to infinity. So I have to truncate either the integral or the sum. So you have to discretize and truncate. Okay, and then those issues, there are problems around that. But the point is, the main point is that the transforms in such a problem are easy to calculate. And contrary to what you would see, because you don't see any of this in the standard textbooks, once you can calculate the transform, you can just stick it in. So the approach here is, you think of, this is just the point. The other way to put this, that the way I think you should first order think of this, is f of t, you can do this transform. And you can then sometimes find the answer. Now the thing you want to think about is this. Okay, now, right? What is this, right? The idea is you have some meat grinder type thing, right? And you don't worry about it. Just like all the other things, the tools we have, you stick this transform in the meat grinder and get the answer out. Whenever you got one of these, you can do it. And you should know that, because it's sort of not standard knowledge, and it's very important in applied probability. If you're doing applied probability, if you look through the probability, you look through Ross, he doesn't say a word about this. Okay? But he does say a little bit about transforms. So if you had the transforms, the important point is, well, having written this down, you say to yourself, what good is that? Right? You don't want to know this. This is just an intermediate step. But if you can take this and stick it in here and get the number out, then you're in business. Okay, that's the point of this, that you can do that. And you can find out how to do that and see how it works fairly quickly. So that's what I'm inviting you to consider in this. And that sort of highlights why what makes this even more important, because you're not stuck here. You can go all the way. Okay, well that's the end of this. Are there any comments? This is the end of the review, and I've taken this much longer than I had planned, but we will now start stochastic process. We snuck in a little stochastic process, so we're now starting stochastic process, Markov chains, so forth. Now we're sort of moving into chapter 4. But, okay. Well, okay, leave this. So happy to entertain. This is sort of like all of a sudden we're going to have major context shift, because I'm now getting to chapter 4. But I wanted to say a little bit, and this is, so you can see, if you haven't looked already, this is one of the projects, the extra credit projects is this. The other two are the stuff about stock prices that I mentioned before last time. So there are these 3 things, and there's a web page for them, and they're there on the web page. Otherwise, if you don't elect to do that, you can almost like let a lead shield cast over this whole discussion, and you're not going to, it's not a major part of the course. Okay, so we can maybe get rid of this. This is such a favorite topic of mine. It's amazing that I managed to get to the end of it before the period ended, because there's a lot more to say. In operations research models, it turns out that it's very convenient to construct transforms of things when you find answers. So this becomes very useful. You decide if you're one of the typical student, you like finance, you get interested in finance here, and you find you want to know how to price options or something. And it turns out that, there's a lot of the stories complex stochastic calculus, and you've got to calculate stuff, but fundamentally, you're trying to calculate a probability distribution. What's the distribution, of the price? What's the probability distribution? Just like this, it turns out it's often relatively easy to calculate the transform of the distribution. So you'd like to know how to invert it. And the main mindset is the realization of the two steps, that it's often really easy to work with transforms, and that you can make it back. Once you do that, you can get back and get the numbers you want. So it's extremely important to know to understand that this is a possibility. It's more important to understand the idea than it is the details. You won't know that you can hire somebody else to do this if you don't know it can be done. Okay, that's one view of this. Okay, now, seemingly on the opposite spectrum of utility, right? Markov-Mouse, leaving the world of practical, getting in there, rolling up our sleeves, and actually calculating numbers, which is numerical transform inversion. We're getting back to probability, and as usual, it's sort of like Ross specialized this in simple examples that seem a little bit stupid. You have to suspend your criticism a little bit. Okay, so we're going to talk about Markov-Mouse. So this is probably, maybe one of these times I'm going to get the criticism. This is going to extract the criticism of the people that are concerned about cruelty to animals at Columbia, which is, I guess, a big activity. And we in engineering have not gotten our share of criticism in this, and it would certainly seem that this is an opportunity for somebody to identify how we're abusing mice. Okay, so we make a maze. Here's a maze. We make a maze, and we have 9 rooms. And we make doors between the rooms from all adjacent rooms. Now, rattling is annoying. Okay, we're making doors here. Some relief from constant lecturing by making the doors. Okay, so we have a door between each adjacent room. So we have 9 rooms. We have this maze. And now we now contemplate the abuse. We put the mouse into the maze in one of these rooms. And the mouse moves around in the maze. Well, I mean, we are fascinated with the mouse moving around in the maze. So the mouse moves around in the maze, and we start thinking about, well, is there any pattern to what the mouse is doing in the maze? What's going on? We begin to pay attention. We put him down here. He moves around and so forth. And we start having opinions about what the mouse is doing and what kind of regularity we're seeing. being probabilistic, we make a model for what the mouse might be doing. A hypothetical model that would be, maybe we would like to say that the mouse is or is not doing according to this, behaving randomly. So the random model would be, you put the mouse here, and you assume as a model what could be doing, the mouse might or might not really be doing this, that the mouse randomly at each room goes through one of the available doors with equal probability. So suppose he's totally behaving randomly. So if he's in one, he picks one of these doors, each with probability half. And when he gets into room 2, he picks each of these 3 doors with probability 1/3. And then when he gets here, he picks each of the 4 doors with probability 1/4. And so on, and gets back here, 9 each with probability 1/2, and he keeps moving like that. Okay, then we ask about, well, what's going to happen in the long run? If the mouse really behaved like that, what would be happening in the long run? So you might say, well, what fraction of time in the long run? What time mean? Suppose you count time as he's in this room, and so forth, and successive rooms that he's in. So it's discrete time. Time n is the nth room he visited. So then you think, well, what fraction of the times does he visit room 2? And you might then say, well, what he does is the mouse's actual pattern over lots of traveling around consistent with that, you might ask. I mean, what the real problem is a little unclear, but for us, we've got a probability model of the mouse moving around in here. And then we want to, the standard thing here is we specify the local movement of the mouse. The kind of one step, we say, well, here's what we assume happens in one step. What happens in the long run? So the question is local, global. This is the question. You assume the local behavior, one step. I assume that when he's in room 2, he chooses each of the available doors with probability 1/3, independent of all the past. And when he's here, he chooses each of the available doors, with equal probability, independent of the past, every time he goes there. So that's the model assumes the local behavior, and then I want to know what happens. Well, first I might want to know what's the probability. If he starts in 1, what's the probability he'll be in room 8 7 steps later? And I want to be able to analyze this model. That's Chapter 4. We can all, I guess we can stop. We could consider ourselves done with Chapter 4. That's sort of the synopsis of Chapter 4 in some sense. Okay. So then what is Chapter 4? Chapter 4 is about analyzing such problems. Okay, so the one thing we do is we formalize this. The standard kind of opening statement would be this. Let xn be the room occupied by the mouse at nth step, or the other word, the nth room visited. That would have been faster. Let xn be the nth room visited by the mouse. And therefore, x0 is where you put the mouse down to begin with, which could have been at random. x0 could be at random or not, could be fixed. x0 is the initial room, and then n is the, well, let's see. So maybe I'm starting x1. First room, nth room visited. I start with x1. Here, I start with x1. There's always an issue about where you initial 0 or 1. So nth room visited is different from nth step. If you count moves, maybe he made no moves. So it's just depends on semantics, how you want to. If we think of number of moves occupied by after nth move, so this is the n plus first room visited, right? Then x0 would be the starting point. That would be more conventional. Start at x0, and then x1 is where he is after he goes one step. Okay, so then we have xn, n greater than or equal to 0. This is a stochastic process. Xn is a random variable because we've assumed the thing random mechanism. Xn is a random variable. Let Xn be the room occupied by the mouse after the nth move. Start at x0. The sequence of random variables, Xn, is a stochastic process. And we want to know properties of this stochastic process, given the assumptions we've made. That's what our goals are. Okay. Now there's a nice reduction. All of this may not bring joy and happiness to you, because there's a reduction of this problem into previous math that you've presumably all studied. And some of you surely wish you forgot, and yet it's going to rear its ugly head again here, as all these subjects do. Okay? So what subject do I want to bring to bear? Yeah. Yeah, linear algebra. And I'm not sure you said that with the right facial expression. Okay? So linear algebra. So all this can be reduced to linear algebra. And so that's one way of looking at this subject. You can kind of, if you know linear algebra really well, the whole thing's trivial. It's all, you know it already. And we got to then the model is going to reduce to a matrix. So once I make the model a matrix, and that's all there is in the model, really, then surely it's got to be linear algebra. But it'll be even more clear when we do that. So we're going to model the transitions, the probability distribution of the transitions as a matrix. And that's going to be entirely equivalent to what I just said in words. So we're going to have a matrix which is, there's P. P is the transition matrix. And we have the states here. There are n states, and there are n states here. And what we put in here, so P12 is a half, and P14 is a half. Can't write that. P12 is this is where you start, and this is where you go. So P12 is the probability of going from room 1 to room 2. And P14 is the probability of going from 1 to room 4. And all the other entries are 0 because you can go here or here with probability half. And so for P2, you'd have P21 1/3, P23 1/3, and P25 1/3. And so forth. So there's a 9x9 matrix which describes the evolution of the system. Every step is understood to be independent, and this matrix describes the transition probabilities. Whenever you're in step 2, independent of whatever else happened in the past, you will go to one of these 3 states with these probabilities, and you just keep doing that. And so now the model is the P. When you make a discrete time Markov chain model, like all of chapter 4, if the state space is finite, the model is a matrix P. Okay, now that's part of the story, why it's all linear algebra. The other part of the story is, well, we want to know what happens not just in one move, but in a lot of moves, right? So 2 moves, for example. So we want to know what's the probability of going from I to J in 2 moves. And we think, well, let's just figure out what that is. We start and we go from I to K, and then we go from K to J, right? So we can go from I to J in 2 moves by going from I to K and from K to J for any possible K. And these will all be separate possibilities, because we will go from I to K, and different K will be different possibilities. So the probability, this is going from I to K and from K to J. And this is in 1 step. And therefore, if I put the same thing here, Pij in n plus 1 steps, same thing. I want to know the probability I go from I to j in n plus 1 steps. It's the sum over k of the probability of going from I to k in n steps, and then going from k to j in 1 step. Totally clear, makes sense, no problem whatsoever. Hopefully this makes sense. Hopefully this is clear. The matrix is the model, and now we're discussing the evolution, how the thing goes 1, 2 steps, 3 steps, so forth. So the thing to observe and the point of view of the linear algebra is, well, we would like this to really fit into linear algebra totally. It's just not just a matrix. That's not going to get you very far. But you would like this to have the property that this corresponds to the nth plus first power of the matrix P. That the multiple steps, so this is P squared Ij. In other words, this is clearly the probability of going from I to j in 2 steps by definition. But at the same time, this is the square of P ijth entry. Different concept. This is the probability of going from I to j in 2 steps. But the same hand, this is exactly the formula for P squared too. So you need to remember matrix multiplication. This is the formula for matrix multiplication. So P to the n equals P to the n. The probability matrix of n-step transitions is just the nth power. That's key to get the linear algebra really to kick in, right? Because you don't want just that the matrix somehow is there. You want the matrix, the operations, right, to be just like linear algebra, that it's all matrix multiplication. So everything, all the multiple steps are just matrix multiplication. Therefore, I mean, you got to know not just about matrix, but you got to know about matrix multiplication. So if you want to know what happens in the long run, you want to know the probability of going from I to j in n steps for is some probability. This is the probability. Well, so you're just raising. The point is you're just raising the matrix to a power. So yeah. So here we are. Let's think about what this is. An example. If we were doing P, if we did this, right, the point that your point is good. I mean, what goes here? So when you do all of this, for this problem, if you're sitting somewhere, these, yeah, what are these numbers? In other words, the simple answer to your question is there is no guarantee that these numbers are strictly positive. They may be 0. And so therefore, this is complicated. So it's easy here, right? If we pick some states, like if we picked, to take your point, well, if we did this, what's the probability of going from 1 to 9 in 2 steps? This is still correct. So I put 1 here and 9 here. But when we do this, we're going to get 0, because one of these is always going to be 0, right? Because we can't go from 1 to 9 in 2 steps. So the entries will be 0. Your point's exactly correct. We can go from 1, in 1 step we can get here, and in 2 steps we can get to 3, 5, 7, or 1. Right? In 2 steps, starting in 1, we can only get to 4 states in 2 steps. That's totally reasonable, yeah. So let's just focus on that. P1, say 7, 2 steps. What's that? You go from 1 to 4, and then you go from 4 to 7. And that's from 1 to 4 is 1/2, and this is times 1/3, right? Probability of going from 1 to 7, going from 1 to 7 in 2 steps. I must go, the only way I can get here in 2 steps is to go from 1 to 4 and from 4 to 7. And therefore, probability of going from 1 to 7 in 2 steps is the probability of going from 1 to 4. It's independent of this, so I multiply. And it's 1/6. Now, it's the same formula here. All the other terms are 0. Does that, in other words, the probability, the important point, maybe I skipped this and thinking of it obvious, the probability of going from some place to another in 2 steps is the probability, you're going to go take the probability of going to one where you can go and the probability where you go from there. And you can consider all possible k. For many choices, it will be 0. Is that, Michael, is that okay? You don't look pleased. So maybe there's something, yeah, push this point. There's a lot of displeasure in the for this point shouldn't be that bad. Maybe there's something that maybe something is confusing that I've said backwards or wrong or something. You all look a little displeased. So maybe there's something.
A rigorous definition of I, J, and K, or your indices.
Yeah, so I would say, indeed, you're saying it in a form that I would be totally content with. Is this formula ought to make you happy that the probability of going from I to J in 2 steps is you think of the picture this way. Suppose you say, here's I. And then I could go to 1, 2, 3, down to 9, right? Because there's only 9 places I could go, which may have 0 probabilities. And from each of these, I could go to 1, 2, to 9. I can go from I to each of the 9 states, possibly, maybe not. This is including more than is possible. And from each of these, I could almost go to 9 places, because I have to go to some room. This is allowing more possibilities, some of which will have probability 0. So then I'm saying, well, the probability, let's say I can go from say if I put 1 here, I can go from 1 to 2, and that's the probability is a half. And then from 2, I can go back to 1, say, which is probably 1/3. So if I wanted to consider going from 1 to 1 in 2 steps, I could go from 2 with probability half and then 1 with probability 1/3. But I could also go from 1 to 4 with 1 to 4 with probability 1/2. And then back to 1 with probability 1/3. So if I wanted to know what's the probability of going from 1 to 1 in 2 steps, it would be P12, P21 plus P14, P41, right? If you think about this, here's the point. If you think, what's the probability of going from 1 to 1 in 2 steps? In the first step, I leave either of these 2 ways. And in the second step, if I go here, I got to come back. In the second step here, I got to come back. So I get P12, P21, I multiply the 2 because they're independent, and I get P14, P41, I multiply because they're independent, and I have these 2 A's. I could have written all the others down like this formula, but they'd all be zeros. Okay? That's the 2-step thing. The n-step thing is the same thing because this is n minus 1, so it's just by induction, recursively. If I put n here, this could be n minus 1. Same logic. Right? So one logic is to actually convince yourself that this formula is the 2-step formula. So be it 2 or 1. It's the same thing. That's the formula. In other words, these are K are mutually exclusive possibilities. From I, you have to go somewhere, and each alternative is mutually exclusive. You go one place. So as you change K, they're mutually exclusive possibilities. And then after you go to K, the next event is independent, so these are multiplied. So this will, I promise you, this will become totally clear. This is indeed what you want to have be totally clear, and this is not the issue. So the interesting part, so what is the problem? So this will not be the problem, even though I don't know whether I'm doing anything. Looks like I'm saying the wrong thing. I have to admit, I see unhappy countenance. Possibly it's that you're ready for lunch, but which is good enough. But at any rate, you don't look too happy. But this is not the difficulty. You think, well, what is the difficulty? The difficulty usually is what is P. The model is P. And once you got P, the operations linear algebra stuff's sort of routine. And now you'll learn all the techniques to calculate everything. However, there's infinitely many word problems whose answer is a P as a first step, of which you can't learn them all. It's not rote. You have to think, right? That's like all these problems. Even though you think you understand the stuff, somehow the problem's worded in such a way it's still hard. And so then, indeed, for a Markov chain like this, if the state space might not be finite, but if it's finite, certainly the model is P. And often the question of what should be P is the problem. The rest of the stuff is pretty routine. So, in fact, I have no way to tell you routinely how to find the right P. That's like, can I give you an algorithm or some method to systematically do all those homework problems, right? Each one's different. It doesn't come, right? You just have to have experience. So the problem, as always, is the word problem in making up the model. That's the problem, as always. You don't want to let the rest of it remain a problem. You want to have it that the rest of it, that the mechanical stuff, the theory, the routine stuff, you know what to do. But the making the P is the hard problem. Here, making the P is easy. This was chosen, but maybe not well, but it was chosen with the intent that the model's totally obvious. 9 rooms, go to the next room, these, specification, the matrix should be totally clear. Okay? Now, to further clarify this, make sure I'm just getting to, so there's an important point. You can escape the numerical inversion. In fact, I'm anticipating that only a few of you will not want to escape but there is numerical homework. And I'm thinking of you doing this in MATLAB. And so you should be looking on the tools web page off the course. And there's actually starting now, there's 2 homeworks. There's one numerical homework. And the numerical homework is primarily doing problems. About half of it is doing problems on this Markov-Mouse model in MATLAB, solving it in MATLAB. So if you've been working with MATLAB, it's elementary, you're just doing stuff, powers of matrices, it will be very, very easy. Moreover, the data and the programs are already there on my webpage, so you don't have to write anything. You may not want to do that. You may want to do your own. It'll be more instructive. But if you know how to use MATLAB, you could do the assignment in 10 minutes. Okay? But there's an opportunity to learn about the stuff. So this means you should be using the computer lab. And on this numerical homework is instructions about what to do and so forth. And you have, for this numerical homework, 2 weeks. So this is like due at the time of the exam. So even though it might take you 10 minutes to deal with this numerical thing, if there's any glitches with the computer room, that could take much longer than the homework. But I'm assuming so the computer lab is in 301, but you could do it elsewhere. You could do it in Butler. To do numerical homework related to this. And that primarily means doing linear algebra. But the data is there online and the programs are there online. So you could just use the programs and use the data and answer the question. However, I encourage you to actually think this through for yourself and do these. I mean, it's linear algebra. It's not hard. I encourage you to just do it yourself as long, if there's... most of you should be able to do this yourself without any problem, and it's probably, and will do it better than I did it. Your programs are likely to be better than mine. So go ahead and do it. But there's 2 homeworks now. One is the beginning of chapter 4, and one is this numerical stuff, which is doing matrix calculations to see what's going on. Okay, there's, as usual, there's a recitation today discussing the second homework, which is to be turned in on Thursday. And what I'm talking about is the third homework, which has 2 parts, which is posted today. Okay. have a good lunch and return. Many of you return at 1 or up to the 11th floor. Okay.